now for something more geotechnical and something more forensic analysis of a failure. This work has been done together with my other two colleagues, Dragoș Găitănaru, Traian Bush, also from the Technical University of Civil Engineering. So let me give you some introduction in this problematic. So we had in Transylvania somewhere a waste management center which was composed of a municipal landfill and a sorting and mechanical biological treatment station, and also an administrative area. In fact, we will talk only about the administrative area, which was the subject of this forensic analysis. It is located in a hilly region, so we have slopes everywhere, and local instability phenomena occurred at some point in some man-made slopes. And they started to remediate this local instability phenomena by several, or going step by step, let's say. First, by geometrical methods, that means introducing berms, reducing the inclination of the slope, and so on. And it didn't work. So, of course, the contractor asked for some more money for remediating everything. And the case ended up in the court of law. The cause has been identified in the earlier stages, that being the unpredictable groundwater presence. Because the geotechnical investigation that was carried on at the very first stages of this project, and also some other supposedly more detailed geotechnical investigation, didn't found any groundwater. So once that this phenomena happened, of course they saw that groundwater was coming. So they said, we were not informed about the presence of the groundwater, therefore it is unpredictable. And this is very important because in the contract of the contractors, there is a special clause regarding the unpredictability, and they are entitled to claim some more money if it is outside, let's say, of their powers. And if it is unpredictable, of course, they were entitled to be paid more for this. Also, what we saw is that several such instability phenomena occurred during the time. They were not very big landslides, so it was not seeming something very seriously, but whatever measure they were taking, it was not enough. So the instability phenomena continuing to occur. They went from the very simple measures, as the geometrical measures, to more complex one, building retaining walls that were supported by micropiles, by ground anchors, drainage works, monitoring, and everything was still moving. So this is why the case ended up in the court of law. The court of law asked for a forensic judicial analysis, and they are establishing normally some objectives, some questions to which the expert will have to answer. The first question was, what is the origin of the water infiltration in the area? And just in bracket, let's say, a comment that lawyers are using a lot of words, let's say. And they were saying, if the cause of this infiltration is the rainwater, but infiltrated outside of the perimeter of this work, this is not our problem. It is outside of our property. Of course, water and soil is not taking into account the ownership of the pieces of land. So this is just something that lawyers are using for winning this kind of process. The other thing was to analyze the stability of the ground, and the most important thing was to establish if the phenomenon was really unpredictable. I was appointed by the Court of Law as an expert, and I immediately saw that the existing geotechnical investigation, especially regarding the groundwater, was completely insufficient, and also that the geotechnical design was very poor. So in order to solve this problem, it was mandatory practically to conduct a complex geotechnical, hydrological, hydrogeological investigation, numerical modeling, including also some unsaturated measurements. Mihalis, you will be pleased to know. So a lot of means, a lot of investigation for finally not so important landslide in terms of size, let's say, but a lot of money also that were in this. So for the geological, hydrogeological, and hydrological setting, we are in the southeastern part of Transylvania, something here, it's almost in the middle. We have some representative formation of bedrock that is a marl that has a general inclination. It is weakly stratified, and it has from time to time some very thin sandy films. And for the quaternary deposits, we have a diluvium, proluvium, and alluvium deposits, mainly clayey soils. From the hydrological point of view, we are in the hydrographic basin of one of the major rivers in Transylvania, Mureș River, but there was also a stream, a very small stream, and it was of interest for the problem. Altitude around 300-400 meters above sea level, and the maximum slope value of the hydrographical basin was 19 degrees. I'm sorry for the mistake there. We didn't find a proper aquifer system, that means consisting of porous, permeable, non-cohesive material, but we saw that in some part of the site there was a gravelly sand which was outside of the limit of the waste deposit with a very small width of 150 meters also, and only appearing in some parts as a lenticular shape. And it was surrounded, and this is important, by sand and gravel, but in clay mass. That means that finally, from a permeability point of view, the most important was the clay. The permeability was as for a clay material and not as for a gravel material. We did a lot of in situ investigation. First of all, geological and hydrogeological boreholes and piezometric wells, geological and morphological mapping, infiltration and hydraulic testing, of course, topographical measurements, geophysical investigations, but also flow and river measurements because we need it for the hydrological model. In total, 4 terrain investigation campaigns were performed with hydrological geomorphological mapping. During the, here you can see some photos taken during the infiltration and hydraulic testing, and here is not the geological and morphological mapping. I put a wrong arrow here, is the hydrological mapping. It's the stream in the area. And during this mapping, we saw some geomorphological processes, evidences, that means cracks and drying fissures, detachment surfaces, and gully erosion and ravine processes. And this red line is showing the area where those evidences were found. Also, we performed tests and measurements in the boreholes that we drilled in the field. That means hydrogeological test conducted using a recovery method, or what we are calling bale test. And also hydraulic test consisting of evaluating what are the infiltration coefficient in the unsaturated area at various locations. And these were performed using the single ring and filtrometer method. And in total, we carried out 13 such tests. Also, some geophysical testing, electrical resistivity tomography, a total length of approximately 2.5 kilometers, and just to illustrate the principle of the method, but I will not insist upon it. And here are just, for example, some of the results of this electrical resistivity tomography that we performed on site. For the hydrogeological monitoring, we had 5 wells that were monitored during a period of 90 days during the autumn and winter season. And we monitor the levels of the groundwater and the temperature, and we obtained such graphs for 5 wells in terms of level and also making the correspondence with the rainfall, and here is the time. So starting from all this data now, we started to develop some models, and first of all, because the water was the main reason of all this, we developed a hydrogeological model, starting first of all from the morphological and topographical model, that means the digital terrain model, which was based on direct differential GPS measurements and also on what we saw directly on the site, the morphological mapping, all the visible cracks and landslides and so on. We had a geological 3D model, which was based, of course, on the digital terrain model, including also lithological data and the geophysical data. Next, a hydrological model, rainfall runoff, which was including land cover, hydrological flow measurements that we performed, the land cover classes and climatological data, and we used the HSSMGE software package. Then, another model was the groundwater flow model based on the hydraulic in situ data, the pumping hydraulic test and so on, the infiltration hydraulic test. And this hydrogeological model was developed in 2 stages. A first general model with a certain time frame, let's say, in steady conditions, and an unsteady condition hydrogeological model to simulate the groundwater flow under different scenarios. Here is the geological 3D model showing the whole area, and our excavation is here somewhere. We can see the marl. On the marl, we have some silty marly clay, and this L3 layer, the gravel and sand, is very, very, it's this one. You can see it's very thin, not everywhere, but is influencing, however, the groundwater flow. And then we have this one, the yellow one is a silty clay and the topsoil. So this is the general lithology of the site and the geological model. The hydrological model, here is the whole hydrographic basin that was of interest with all the tributaries and the main stream. We had a watershed that was divided into 18 sub-watersheds of different sizes, and they were based off surface runoff accumulation, and here you can see the areas, the limits of the areas in terms of surface for these 18 sub-watersheds. And here is what the model considered, the average slope for each sub-watershed, the land use and the soil type, the surface runoff parameter, considering the SCS method, the base flow, and also the rainfall. Another model was the hydrogeological model, and this is just one of the just one of the images of the 3D representation of the groundwater table. We use this value for the permeability coefficient, the porosity, and the effective porosity. Due to the lithology and also due to the presence of some fissures, the cracks that we saw on site, and these cracks were, the size of these cracks were about centimeter-sized openings. The hydrostructure is an aquitard and was considered with a free water level. So there is no aquifer, but it is an aquitard. And here are the isolines of equal potential for the steady state condition for our hydrogeological model, and we can see all the values of the hydraulic head. And we developed another one considering the existence of some drainage measures, because, as I said before, they included at some point some drainage measures, seeing that water was coming on the site and worsening, let's say, the stability of the slope. And another model was in unsteady state after several duration, and this is just the picture with isolines for after 720 days. What were the conclusions of this hydrogeological analysis? First of all, that the hydrogeological model we developed was accurate because it was confirmed by the field measurements that we had. We also concluded that the average annual flow of the flow rate of the groundwater is ranging, it's not much, but it's ranging between 0.5 and 1 liter per second. But during the dry periods, the flow rate drops below 0.5 liter per second. And this flow rate is very variable, ranging from 0.1 liter per second to 1.8 cubic meters per second during the rainy period. Except for the upper horizon of yellow clays, groundwater was identified in all layers, in all lithological types of clay or marl nature at the bottom. And this is why we consider all together as a unique single hydrostructure when we defined our hydrological model. This hydrostructure is an aquitard and not an aquifer, due to the fact that we don't have granular materials and so on. And what is the most important is that it has a very slow dynamic. That means that an infiltration happening in upstream will be received in downstream area after a long period of time. And this was the main problem, because during the geotechnical investigation, we are never waiting enough time in order to capture what is really happening. This is why it's so important to have a hydrogeological monitoring over a sufficient long period of time, because if not, we are not capturing those phenomenon, and we will get to the wrong conclusion that there is no groundwater at all in the area. And this is what they did. From the hydrogeological model in steady state, we tried to model what happened before the landfill was built, the initial situation. We obtained the recharge value of the hydrostructure, which is due mainly to the groundwater flow coming from upstream to downstream, and this was of 88 cubic meters per day. The vertical recharge from rainwater was low, only 4 cubic meter per day, and this is due to the high slope of the area. I remind you that we are in a hilly area, so much of the water is running off, and the vast majority of the recharge of this aquitard hydrostructure is coming from the groundwater flowing from upstream to downstream. But this recharge rate may increase when we have those contraction cracks, and I will develop a little bit later. Water is coming more easily through the cracks, therefore increasing this recharge rate. After all this, we geotechnical engineers came into the analysis, and we performed geotechnical analysis. Of course, we had geotechnical investigations, and they were performed in many stages. Only for this forensic analysis, we didn't do much, only a kind of confirmation of the nature of the soils. And the conclusion, because of course I will not present everything, the conclusion was that, as always, almost in landslides, we had a cumulative effect of natural and anthropogenic aspects. Among the natural one are the characteristic of the site lithology. That means swelling clays. This was the main finding of the geotechnical analysis, that those clays that I showed you before were swelling clays, and they were laying over the marly bedrock. And this was proved also by the presence of those cracks on site. The groundwater presence is now, we know that the groundwater is there, and of course this is influencing both by increasing the water pressure in those cracks and also by reducing the shear strength of the clay after the water is infiltrated into the ground. The water that is infiltrated into the soil is drained very slowly due to that aquitard type hydrostructure, low hydraulic conductivity, slow dynamics. On the part of anthropogenic aspects, the excavation, the earthworks were performed on site, and this create finally a drainage path for the water that was accumulated in the ground, which of course outflowed in the excavation on the slopes and ran off, and this produced the local instability. The swelling clays, of course, led to contracture fissures, cracks, through which rainwater could infiltrate into the soil. And also among the anthropogenic aspect are the slope inclinations, which were too steep with regard with all the above mentioned soil and water conditions. The geotechnical investigations that were performed on site were in total 6, 3 before the instability phenomena and 3 after the landslide occurred. There was only one hydrogeological investigation, but it was not for the geotechnical purposes, let's say, but also only for water supply. And they saw what we know already, that there is not much water and only that length of gravelly sand could be used for water supply for the site only. None of the 3 geotechnical studies before the phenomena emphasized the stability problems of the site or the groundwater infiltration or the presence of the swelling clays, and they didn't see any erosion processes, evidences on the site. So it was poorly done, for being honest. Also, they didn't perform stability analysis prior to the instability phenomena. Once that this happened, they performed a first stage of stability analysis, but only using horizontal stratification, horizontal lithology, without taking into consideration the real disposal of the layers, and without groundwater, because they didn't find any during probably the summer, and because they didn't wait enough time. Of course, everything was good. So some very small measures were taken after this stability analysis. Also, the slope inclination didn't take into consideration the specific behavior of swelling clays. And here I have to develop a little bit more, because in Romania we have around 10% of our territory subjected to swelling clays. We have a special norm for this, for constructing on such terrains. And the most important thing when building slopes, man-made slopes, either for embankments or cuttings, is that the swelling clays will be exposed to the atmospheric factors, and therefore they will reduce progressively the shear strength until very, very, very low values. That means 2, 3, 5 degrees the friction angle. This is why there is a recommendation in this technical norm that the slope inclination should be 143 or 144, that means vertical over horizontal, and in our case it was 141.5. The maximum height was 26 meters and no berms. And there is a good practice, let's say, to have a berm every 10 meters, more or less. So everything was wrong from every point of view, even though we know already this. It is not the first time we are constructing something in swelling clays and so on. So after the first local instabilities occurred, they performed another geotechnical analysis, as I said before, but using horizontal lithology and no groundwater. Also, let's say that indeed they didn't find groundwater in the boreholes and they didn't wait enough in order to capture the slow dynamics of this hydrostructure. But there is a good practice when we have clays and we are performing stability analysis to consider also a saturated condition of those clays, because this can occur during the service of that slope. And this is, of course, according to Eurocode 7. We have also a national guideline to apply Eurocode 7, which is, again, requiring this, a saturation hypothesis. And as I mentioned before, the swelling clay's presence requires to check also the stability, including those very, very low shear strength parameters due to possible contact with water. But also, we saw, and this is another lesson that we learned, that our national technical norm on geotechnical investigation, which was in force at that date, had indeed some provisions with regards to hydrogeological data, but only requesting to provide the groundwater level and the type of aquifer, the possible excess pore water pressure, and to provide hydrogeological cross-sections. I must say that this is not current in Romania, even though we have groundwater, we are not in the desert, so, but even though it's not current to have hydrogeological investigation every time that we are performing a geotechnical investigation. And just for joke, someone was saying that only Loretta is doing hydrogeological investigation in Romania. Of course, this is not true. It's becoming more and more popular, but even like this, it is not done systematically. But also our technical norm is referring to Eurocode 7, Part 2. And in Eurocode 7, Part 2, there are many, many provisions covering also this situation with an aquifer type and not a classical aquifer and so on. But no one is reading anymore that. They are only reading the national document, and even though there is a reference, they are not going to that reference to see whatever it is there. So we found out that only on our side, let's say on our legislation side, there are things to be improved. Okay, for the geotechnical analysis now, we had consolidation measures, but nothing worked. And it is like in our legend, and Romanian people know, the legend of Manole, and everything which was built during the day was collapsing during the night. It was like a trial and error approach, let's say. Let's try this one. Okay, it is not working. We will do something more. Because, of course, the contractor was interested in spending as little money as possible. So in the first stage, they just reduced the inclination to 2.5, but as I said before, normally it's 1.43 or 1.44. They included also 2 berms for the 26-meter height slope. They performed some drainage works in one corner of the site, also some collection of runoff water on each berm, and they protected the surfaces against erosion. In the second stage, they saw it's not enough. They included sub-horizontal drainages, drainage trenches, and also some retaining walls that they were disposed in saw-teeth. That means on one berm here, on another berm there. So there was not continuous on the whole height to have consolidation measure. In some area was at the upper berm, and in some other area on the intermediate berm. So it was not, let's say, adapting to all the situation that can appear. Those retaining walls were supported by micropiles. This was not enough again. They put also some ground anchors, and some of the ground anchors were not built, saying that if there is a necessity to include another ground anchor, we will do it then. So at every stage, it was, of course, a preoccupation about the cost and so on. Also, they started some monitoring, and this is a good thing. And they saw that it's still moving, so in the third stage, new intervention on the retaining walls had to be taken, including those additional ground anchors and so on. Also, new drainage works were done because probably during the time some more rainy period occurred and they saw other areas of the site with water infiltration. In terms of stability analysis, this was very classical with limit equilibrium method, and we checked both circular slip surfaces, polygonal slip surfaces at the contact with the marl, and also these hypotheses regarding the shear strength parameters reduced at 30% of the peak values. That is the recommendation in our national document. We reconstituted the initial slope, and we saw that the initial natural slope was stable in almost all situations, except for this drastic reduction of the shear strength parameters, but this is not relevant for the initial natural slope. The clays are not normally exposed to the atmospheric factors. Also, so we concluded that for sure the causes are related to the anthropic factor, to the works that have been done and the errors that were done at the design stage. When man-made slope with their initial inclination of 1/1.5, of course we can see here many red values indicating that there are some design situations where the stability is not fulfilled. And we can see here some of the slip surfaces for the initial design, and this is the remodeled slope with now 2 berms included, but even for this remodeled slope it was not enough. And we can see here the groundwater level that was determined, so this is not the saturation, complete saturation hypothesis. So, what were the conclusions for this very current and common stability analysis? Is that the groundwater was the primary cause of instability phenomena, and of course the design should have considered it. There were the basic design errors, slopes too steep and without considering the presence of swelling clays. And also, they didn't consider that water can enter to the contraction fissures present on site, and this will reduce drastically the shear strength parameters. The remodeling interventions that they took, the berms and reducing the inclination was not sufficient. So they have introduced 39 sub-horizontal drains for collecting groundwater, 46 segments in AUTH of reinforced concrete retaining wall, each segment being supported by 5 or 6 micropiles and 3 or 4 pre-tensioned ground anchors. And despite all these extensive consolidation measures, they still didn't consider the swelling characteristic of the soil, and no detailed stability analysis were performed showing that, in fact, all those measures are effective. So, in some sections, the consolidation measures were not effective, and because they were not deep enough, because they didn't perform any calculation, and they were not located properly. And the monitoring showed this, and at the date of the analysis, that means in 2019, that means 2 years after the intervention, displacement still occurred, and during my site visit, I saw this sign of, again, instability, and also this is consistent to this monitoring plan, let's say, with some values. This is consistent with this point, 313, and you can see here that it's still moving, and the red arrow is showing, and the yellow arrow is showing the direction of the movement that was determined during the monitoring. We are coming now to the most important part, the unpredictability. And this is a very long discussion. What is predictable and what is not predictable? So the lawyers will see something else. Thus, we, geotechnical or engineers in general, we are seeing in all those phenomena. But for me, I analyzed the lithology, and this is mainly an upper clay layer over a marl bedrock, which is prone to instability. And this is well known because in the whole hilly area of Romania, we are facing this. This is not new. This is not something that we don't know. And if the water infiltrates on the contact in between the clay and the marl, this is diminishing drastically the friction angle up to 2-3 degrees. So it is slipping like on the soap, if you want. Groundwater, of course, excess of pore water pressure in the fissures, reduction of the shear strength parameter, slow drainage due to the geological and hydrogeological features of the site, and the slow hydrostructure, the aquitard. The excavation works that were performed on the natural slope were leading to a drainage path for the water that was accumulated into the ground. The swelling clay presence leading to drying fissures through which rainwater infiltrated easily. Improper hydrogeological investigation, no long-term hydrogeological monitoring. And we agree, all of us, that the aquitard is a hydrostructure that is difficult to be identified. The design didn't consider the site condition and designed too steep slopes, improper stability analysis, non-respect of the national legislation in terms of swelling clays, and non-respect of the good practice for considering a saturation hypothesis in the slope stability analysis, and they took no measures regarding groundwater. Of course, we acknowledge the fact that with regard of the hydrogeological investigation, the national legislation was not very clear, sometimes separating the geotechnical investigation from the hydrogeological one, and we learned from this, and in 2022 we revised our national legislation for geotechnical investigation, and we hope that now whatever provisions we put there will be clearer and will not lead anymore to such situation. So a combination of natural and man-made cause, but this is important, this could be avoided by proper investigation, proper design, considering the good practice and so on. So my conclusion was that this cannot be considered as unpredictable, yeah, because if you are following the guidelines and the good practices, will cover this situation. We are not absurd to hope that in all the geotechnical investigation we will stay for 3 months at least to follow, to monitor the groundwater. But considering a saturation hypothesis, you are not obliged to do it like this if it is not very important for the job, but you will be covered. So we performed a very complex forensic analysis of this instability phenomena, which were not very complex finally. It was local instability, quite benign, I would say, but leading to a lot of money put in those remediation measures. So despite of this first impression of simplicity, cut slopes in clay soil, it showed a hydrogeological specificity, which was not so easily identifiable during the investigation. We had the geotechnical specificity, swelling clays, but again, this is not something never saw in Romania. But we had also an improper investigation and design and non-respect of good practice and legislation, combined with a lack of clarity in the technical norm. It required a complex investigation, analysis, and numerical modeling, and highlighted also the very important aspect of the good cooperation between geotechnical engineers, geologists, hydrogeologists, and the need for long-term monitoring, which is rarely done due to time and financial constraints. Of course, there is a big discrepancy between the price that was normal, let's say, for a proper hydrogeological investigation and monitoring, and the price that was paid for all these extensive measures, which are still not enough. Everything is still moving. So all these were not enough for stopping the phenomenon, and they should take some more measures. I am not sure that they did. I am not aware anymore about what is happening. I am persona non grata after this conclusion, so I don't know exactly what is happening in the area. My personal guess is that it's still moving, because I saw the design, I saw the calculation, they are not enough, and it is not enough what they did there. And I think that the importance of that job site is not big enough in order to put some additional money again for some more consolidation measures. So my final remark would be that let's put the right amount of money for the right amount of investigation, geotechnical and hydrological, if this is relevant for the job site and so on, because it will cost for sure much less than all these kind of measures that we will have to take after. And with this, I'll conclude, and thank you very much.